All right, we have section 12.3. We are going to do some double integrals in polar coordinates, okay? And man, do we hate polar coordinates because it's something that we're not used to, but man, does it make some of these things in space so much easier. So, think about the universe and the fact that so many things follow circular paths, and our rectangular coordinate system just doesn't work very well in some contexts. And definitely think about like in space when you're talking about how things orbit. We get real stuck trying to use rectangular coordinates there. So a lot of times polar coordinates can simplify things for us as much as we might not want them to. They do. So remember, we can convert from polar to rectangular. R squared equals x squared plus y squared. So you're always going to be looking for those x squared plus y squareds in rectangular, which would indicate that we could switch to polar pretty easily. And then x equals r cosine theta, and y equals r sine theta. And those are the ones, those conversions that we're going to be using a lot. Remember, theta can be, the tangent of theta would be y over x. But we don't use that one as much. It doesn't come up very much, okay? So we will be looking at regions, okay, where it's not x and y values, it's r theta values, okay? And r is between two values, okay? And theta is between two values. We use those Greek letters to represent our angles, right? So we're going to do that. Most often, r should be a positive number, okay? Because remember, if it's a negative r, actually we could just write it with a different theta, right? So, if we have a point at negative 2 pi over 4, okay, so you'd go to your pi over 4, and you'd go 2 units in the negative direction. Okay, it might be right there, but what we can do instead is just write that as r of 2 theta 7 pi. 5 pi over 4. And that's how you're going to see that more often, okay? And then the difference between alpha and beta should be less than 2 pi. Okay, otherwise we've gone around the circle more than once, and we should not do that, okay? So we're going to do some conversions here. You might have a region fxy dA. So this is what we just got done doing. We're going to convert it. And I guess I should say, I'm going to leave it how it is right now. AB. F will be a function of r cosine theta, r sine theta. And then instead of dA, remember dA was dx dy, right? Or dy dx, didn't matter, okay? We're going to switch that to r dr d theta, okay? And of course, you're all wondering, where did that r come from? Why can't we just switch to xy to r theta? Where's that extra r coming from? So I'll kind of show you. There's a couple of different ways to kind of try to explain it at a pretty basic level. I'll go with one of them. But let's keep in mind, okay, so if you had, maybe the region that you're looking at is like a ring, okay, and we're looking at this ring, and we want to find, the area of it or some volume above it. It wouldn't make a whole lot of sense for us to think about little rectangular pieces of that ring, okay? What we really want to do, here, I should do it, where it's a dx and a dy, and we'd have a equals dx dy, or sorry, dA, okay? It doesn't make a whole lot of sense in a curved region like that when we have polar coordinates, okay? And we can have that same ring to it, okay, it makes so much more sense to have these kind of little wedge pieces. Okay, I'm trying to draw it. It's kind of like a wedge piece. And here, let me like zoom in. It would look like this. Okay, where we'd have an R1 and an R2, right? Because that's how you measure your polar coordinates, is like a radius from the origin. Okay, so this would be at a distance from the origin of R1, okay? And then the outer one, oh, that's silly because of that. That one looks like R1. I know, I'll use a different color. This would be R1. This would be R2, okay? And then we would have theta 1, okay, which would actually be alpha. And then we would have, let me get a different color here. We haven't used green. Then we could have theta 2, which would be like your beta, okay? So then rather than going from x1 to x2 and y1 to y2, we go out a distance from r1 to r2 and from alpha to beta, or theta 1 to theta 2, okay? So that would make our little piece here, let's see, this side here would be dr, okay? And then this angle here would be d theta, okay? So let that soak in a little bit, okay? And now to find the area of that, that's a sector of a circle, right? It's kind of a piece of that. So what you could do is find the bigger pi piece that goes out to R2 and then subtract that inner pi piece that goes out to R1, and we'd have the area of our wedge there, okay? So that area would be whatever d theta is out of 2 pi, okay? And then times pi times r2 squared, right? That's how you find the area of a sector of a circle. And that would, again, that would give us that bigger pi piece out to R2. Okay, and then if we subtract out that smaller pi piece that only goes out to R1, then we'd have our little wedge that we want. Okay, and so that smaller pi piece would again be d theta over 2 pi, pi times R1 squared. Okay, you can see that our pi's cancel out, and our d theta over 2 can be factored out. So the pi's cancel out. We'd have d theta over 2, r2 squared minus r1 squared. Okay, so there's our area. We're going to get a little tricky there. D theta over 2, we have a difference of squares there. R2 minus R1, R2 plus R1. Okay, well, what happens is if these get infinitely small, then R1 starts to approach R2. Okay, as that happens, then this becomes our infinitesimally small dr, that tiny, tiny little difference in the r's, and this comes closer and closer to 2r if they start to be the same thing. Okay, so then we'd have d theta over 2 times, I'm going to switch the order there, 2r times dr. The 2's cancel out, and we have r dr d theta. There's where that extra r came from. Okay, there's other ways to kind of derive that relationship, but I think that one, I like that one the best. So there you go. Or you can just take my word for it. You need the r. You can't just switch dx dy to gr d theta. You have to have the r. Okay. So let's get to some examples here. I mean, that's basically the general idea. Now we just need to do some examples where we have things that are given to us in rectangular, and we switch them over to polar. So the first one we're going to do, and again, these are all going to be some examples that are even problems in your book, so you can always look at them too. The first one is going to be number 8. If I ever switch books, I guess I'll have to change these videos. But this would be number 8, and it asks us to compute the integral over the region R of 2x minus y dA. Okay, you've been doing this in the last section. We've seen this before, okay? But they're going to say R is enclosed by x squared plus y squared equals 4, okay, in quadrant 1. So this is all given in the problem. And x equals 0 and y equals x. Okay, so now let's think about that region R. Okay, so x squared plus y squared equals 4 is a circle with a radius of 2. So we'd go through at 0, 2, and only in the first quadrant. 2, 0, centered at 0, 0. Okay. Ooh, a little shaky there, but there you go. Okay, and then in addition to that, x equals 0. So that, again, they told us the first quadrant anyways, that's fine. Okay, I guess we needed that because it's also y equals x, so we needed to know which direction to go on that. Okay, so this is our region. Okay, that's not a region that we want to deal with in rectangular coordinates. All right, this is a region that we definitely want to switch to polar. All right, so think about that. X squared plus y squared equals 4. That's the same as r squared equals 4. Okay, r squared equals 4, or r is just 2, right? And we always want r to be positive because we can get the negative ones with different angles. If we're enclosed in that circle, then we are between r being 0 and r being 2. Okay, if you think about that, if I were to just graph this equation, a polar graph where r is between 0 and 2, that is going to be my entire circle centered at 0, 0 with a radius of 2, and it's going to be the interior of it and the boundary. Okay, now we only want this little pi piece here. Okay, and we know if the line is y equals x, that's pi over 4 to pi over 2. Okay, so we're going to take it at pi over 4 to pi over 2, and then all we have is that pi piece that we want there. Okay, so there are our polar limits. Okay, so next thing we can do is we're going to have the integral. Now, just like with rectangular, we can switch the order, and we can kind of mess around with this a little bit. All right, I'm going to do the 0 to 2 for the r, and the pi over 4 to the pi over 2 for the thetas. Okay, so then I'll have at the end d theta dr with the r. Okay, and then I have to switch this. So x equals r cosine theta, and y equals r sine theta. So I'm going to have 2 r cosine theta minus r sine theta. Okay, so this is the integral that I want to do. Okay. So there's actually three different ways I can do this integral. Okay, I can do it how it is. So let's do that first. I'm going to integrate with respect to my thetas. But first I'm going to take that r out of the interior. So 0 to pi over 4, pi over 2. 2 cosine theta minus sine theta, r squared d theta dr. Okay, so integrate with respect to theta first. So I would have, let's see here, 2 sine theta plus cosine theta times r squared, evaluated when theta equals pi over 4 to pi over 2 dr. Okay, so my integral from 0 to 2, 2 sine pi over 2 plus cosine pi over 2 minus 2 sine pi over 4 plus cosine pi over 4. And I ran out of room, r squared dr. Okay, so then I'll have my integral from 0 to 2. Let's see, the sine of pi over 2 is 1. Cosine of pi over 2 is 0. Minus 2 square root of 2 over 2. Minus, so I can just root that negative, square root of 2 over 2. R squared dr. Okay, so then, let's see, I'm going to have 2 minus 3 root 2 over 2. Let's just make that a simple, no, you know what, I'm just going to leave it. Okay, so then we have the integral from 0 to 2 of 2 minus 3 root 2 over 2, r squared dr. So that would be r cubed over 3. From 0 to 2. Okay, and I know if I plug 0 into that, I'll get 0. So I'm going to plug 2 in, and I get 8/3 2 minus 3 root 2 over 3. A lot of times what you'll see there is we might factor out, what do we want to do here? I would factor out a 1/3. So then we'd have, and this should be 2. Sorry, that's why I was it's like, what did I do there? I'd factor out a 1/2. Okay, so if you factor out a 1/2, then you have 4/3, 4 minus 3 root 2. Okay, but there you go. There's your final answer. Okay. Now, as I was saying, we could do it the other way too. We could also do this as the integral from pi over 4 to pi over 2, integral 0 to 2, 2 cosine theta minus sine theta, r squared d theta dr. Okay, and with that, you would integrate with respect to, I want a dr d theta. You could integrate with respect to r first. Okay, and that would go from 0 to 2, and then d theta. So then we would have the integral from pi over 4 to pi over 2 of 8/3. Okay, and then we can integrate that with respect to theta, and I will leave that to you to see that we would get the same answer. Okay, and then the other thing that we can do, and this one is really handy and a lot of people forget to look for it. This is completely separable. So we could do the integral pi over 2 to pi over 4 to pi over 2 of our theta part. And just multiply it by the integral from 0 to 2 of r squared dr. Okay, so remember, if you can separate the variables like that, you can just completely separate the integrals. And I will leave it to you to see that it will be the same answer. Okay. So there's 3 different ways to do that one. So check them out. Okay. Let's move on to another one. This is number 12 in your book. Okay, we have the integral over, they're going to use d here. Just because specifically it's a disk that they're going to use for their region. They could use R2 if they wanted to. They're just being a little bit more specific. Okay. And then they tell you that D is the disk centered at 0, 0 with the radius 2. Okay. Which just means it's a circle. Okay, it's like we were just showing up there. Disk centered at 0, 0 with a radius of 2. That would be r is between 0 and 2. And theta is between 0 and 2 pi. Okay, so now what we can do too is just remember x squared plus y squared would be r squared. So we'd have the cosine of r. Okay, so we can do the integral from 0 to 2, integral from 0 to 2 pi, cosine r times r d theta dr. Okay, and this is another one too where we can separate it. We can do your integral from 0 to 2 of r cosine r dr times your integral from 0 to 2 pi of d theta. I'm getting a little glitchy here. Okay, all right. We are going to have to do integration by parts with that r cosine r. So remember the integral of u dv is uv minus integral of v du. Okay, so when you have trig like that, right, when you have an algebraic expression and trig expression, that will be a good one to use it for. So we would have u equal to r, dv will be cosine r dr. Okay, so then du is dr, and v would be sine r. So then we would have u times v, so r sine r, minus the integral of v, which is sine r, du, which is dr. So we'd have r sine r. The integral of sine would be negative cosine, so then we'd have plus cosine r. Okay, we'll evaluate that from 0 to 2. So we'll have 2 sine 2 plus cosine 2 minus 0 plus cosine 0. Cosine of 0, oops, let me get my parentheses there. And cosine of 0 is just 1. So we'd have 2 sine 2 plus cosine 2 minus 1. Okay, and that's just for that first integral. Now for that second integral, the integral of theta, or d theta would just be theta from 0 to 2 pi. So that'd be 2 pi minus 0. So just 2 pi. Okay, so in the end, we'll have 2 pi times our 2 sine 2 plus cosine 2 minus 1. Okay, these aren't so bad, right? Okay, let's see, I've got just 2 more examples. It's kind of a shorter lesson. It's not too bad. Okay, the next one we're going to look at is number 16 in your book. This one gets a little trickier, but you just got to kind of think about it. We want the volume inside the sphere, x squared plus y squared plus z squared equals 16. Okay, and outside the cylinder, x squared plus y squared equals 4. Okay, so now let's kind of think about what that looks like to the best of our drawing abilities here. Okay, so our sphere is going to be centered at 0, 0, 0, and it will have a radius of 4. So your sphere, 0, 0, 0, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So there's kind of your equator of your sphere. And we go up and down. Okay, it's not awful, right? Okay, but there's your sphere. And now the cylinder, it goes on forever in the z direction, and its part, its cross section would be a circle centered at 0, 0 with a radius of 2. So that cylinder would basically look like this. Okay, but keep going, forever. So we want the volume that is inside the sphere but outside the cylinder. So if you can kind of think about that, that piece. Okay, so we can do inside the sphere minus inside the cylinder. And that will give us in the sphere but out of the cylinder. Okay, so again, we'll take the volume of that blue sphere, and then we'll subtract the volume that's inside the cylinder, and that will give us the volume that's outside the cylinder. Okay, so now what we kind of want to do here is think about like where the top of the sphere would be in the cylinder, and we're going to find the volume between our xy plane and that surface. Okay, so in other words, the surface z squared would equal 16 minus x squared minus y squared. So z equals the positive square root of 16 minus x squared minus y squared. That will give you the upper surface. Okay, so if we can integrate under that upper surface here, it'll give us the area between, again, like the top of the sphere that's inside the cylinder and then your xy axis. And because of symmetry, we could just double it. Okay. So I hope you're with me on that so far. Okay. So we are going to integrate z, basically. Okay. And then that inner surface there is going to be, we want that disk there again. Okay, and that's the same disk that we've seen in a couple problems now, where r is between 0 and 2, and theta is between 0 and 2 pi. Okay, so that's your region in your xy plane, and we want to integrate it under that sphere. Okay, so we'll go from 0 to 2, r dr d theta, 0 to 2 theta. Okay, good so far? All right. Now, z is the same as the square root of 16 minus r squared. Okay. So we're going to do the integral from 0 to 2 theta, 0 to 2 of r, and that's this r here, square root of 16 minus r squared. That's going to be a nice u sub for us, dr d theta. Okay, and remember that will give us the volume, again, the upper half that we want, and we'll double it. And then we'll subtract it from the volume of the sphere to get the volume that's outside of that, actually. Okay, so we're going to take the volume of the sphere and subtract that from it. Okay, so we're going to start with the integral first, though. Okay, we're going to worry about doubling it and subtracting it later. So for that integral, u could be 16 minus r squared. Remember, take the biggest chunk you can. Du would be negative 2r dr. Okay, so when we integrate r times the square root of 16 minus r squared, okay, we can change our units there. So u would be 16 minus r squared. Here it's from 0 to 2 dr. So that'd be the integral from, if r is 0, we'd have 16. And if r is 2, we'd have 14. And then we'd have the square root of u du. That gets your square root of 16 minus r squared times r dr times a negative 2. So we need a negative 1/2 up front. Okay, so then we'd have negative 1/2. Integrate u to the 1/2, so u to the 3/2 times 2/3. And we'll evaluate it from 16 to 14. Okay, so So these 2's are going to cancel out, so we'll have negative 1/3, 14 to the 3 halves. Did I mess that up? That should be 12, right? Yes, that should be 12. 12 to the 3 halves. Ah, look at that. Minus 16 to the 3 halves. And we can simplify those a little bit, and we should. Okay. Let's see. 12 to the 3 halves. We could split that up into let's see here. The square root of 12 would be the square root of 4 times 3, so 3 square root of 2. Nope, I mixed that up. Yep. 2 square root of 3. Getting glitchy. Come on. 2 square root of 3 cubed minus the square root of 16 is 4. 4 cubed is 64. Okay. There we go. And that was just the inner integral, right? So now we need to integrate that. I'm going to go over here. Integral from 0 to 2 pi. I'm going to take the negative 1/3, 2 root 3 cubed minus 64 d theta. It's just a constant there, right? Okay, so negative 1/3, 2 root 3 cubed minus 64 times theta. Theta goes from 0 to 2 pi. We just need to throw a 2 pi out front. Okay, now remember we need to double it, and we need to subtract it from the volume of the sphere. So remember the volume of a sphere is 4/3 pi r cubed. And in this case, r was 4. So let's see, 4 cubed is 64 times 4, right? It'd be 256. 4 times 4 is 16 times 4, 64 times 4, 128. Yep, okay. So we would have 256 pi over 3 minus twice that, okay? And let me see here. It's going to get a little messy here, isn't it? It's going to be minus twice that. Here, I'm going to distribute that. It would be a positive 128 pi over 3 minus 4. Oh boy, it is really getting messy. 2 cubed would be 8. Okay, so your 2 cubed would be 8 times negative 2 would be 16 pi root 3 over 3. Okay, so we're going to subtract from that. Oh, and we have to do twice that, right? So we're going to subtract 256 pi over 3 minus 32 pi root 3 over 3. Did I get that right? Yeah, I think I did. I feel like I made a mistake there somewhere. But maybe you guys can help me. Oh, that's good, because then those cancel out, and I have a positive 32 pi root 3 over 3. But the answer is just 32 pi root 3, I believe. So I think I added a 3 in the denominator where I might not have needed one. Unless my notes were wrong. Let me see here a second. 2 pi over 3. I think my notes might have been wrong. Let me think here. 128 pi over 3. This is the piece that I'm looking at. Oh, I left off the cubing there. There we go. The square root of 3 cubed. Okay, so that would be, let's go back here. It would be 16 pi times 3 root 3 over 3. Okay, so the 3's would cancel out. There we go. So I don't need that 3, and then that's the 3. There we go. Sorry about that. I missed that. The cube root of, I cubed the 2 to get 8, but then I didn't cube the square root of 3. Okay, that's where we got it. All right, we're going to do one more example before we're done here. And this is number 24. Okay, we're going to do the integral from 0 to a, integral from negative square root a squared minus y squared, 0, x squared y dx dy. Okay, and we're going to convert this to polar to do it. Okay, so we can get some pieces here. Definitely we know how to switch the x squared and the y, but let's take a look at that region. So in our region, these are the x's. So we're between x equals 0 and x equals negative square root of a squared minus y squared. And then we're also between y equals 0 and y equals a. Okay, so this is the piece that might give you a little bit of confusion there, okay? But remember, that's just a circle, okay? And we're looking at negative x values, so we're looking at a quarter of a circle. If I square both sides, I would get x squared equals a squared minus y squared. So x squared plus y squared equals a squared. So it's a circle centered at 0, 0 with a radius of a. But keep in mind, we only want the negative x values. Okay, so we're doing a circle with a radius of a, but we're only looking at the negative values. Okay, so that's the only piece that we want there, only the negative x's. And technically, we could go below. Okay, but we also want to be between x equals 0, y equals 0, and y equals a. I'm sorry, I mixed those up. X equals 0 is the vertical line, y equals 0. So we want this region here. Okay, so that's a much easier region to do in polar. So if we switch that to polar, that's just r is between 0 and a, whatever a is, and theta is between pi over 2 and pi. Okay, which also means, let's see here. I think we're good. Okay, so we're going to do the integral from 0 to a, and the integral from pi over 2 to pi. Okay, and x squared would be r squared cosine squared theta. Y would be r sine theta. And then we have our r d theta dr. Okay, so we've got 0 to a, pi over 2 to pi. We have an r to the 4th, cosine squared theta, sine theta, d theta, dr. We can split this then. We can separate our thetas and our r's. So the integral from 0 to a, r to the 4th, dr. Integral from pi over 2 to pi, cosine squared theta, sine theta, d theta. Okay, so we'll have r to the 5th over 5 from 0 to a. So a to the 5th over 5. Okay, and then over here, I'm going to want to do a u sub, where u is the cosine of theta, du is the negative sine of theta. Okay, so I'll do my integral If u is the cosine of theta, the cosine of pi over 2 is 0. The cosine of pi is -1. Okay, and I'll have u squared du. Oh, forgot my d theta over there. Make it negative. I'll have negative u cubed over 3 from 0 to -1. I'll have -1 cubed over 3 minus -0 cubed over 3. So that's all just 0. So I'll have 1/3. So I'll have a to the 5th over 5 times 1/3, which is a to the 5th over 15. Final answer there. Okay, and that's it for this lesson then.